All right, so let's get started. So let's talk about exponentials and radicals because that's a great place to start before we dive into log functions. Um, Let me open up my cheat sheet. There we go. All right. So here we are with exponentials and radicals. Oops, wrong button. There we go. All right, so let these be some real number. We're gonna only deal with reals for a second. It can also be a variable, but the variable will be a real variable, so it's still technically a real number. And n is a natural number. So here we're going to let these be natural numbers. You remember what natural numbers are, guys? Yes, no? Nothing. I'll just remind you. Anything above zero, yeah, basically. So natural numbers, so this is from like this would be the first day of notes if we were doing a traditional one. So natural numbers include 1, 2, 3. So everything above zero is right. So they're integers above zero. And the reason we're doing integers above zero right now, even though we do negative exponents, right? Um, it's because can we take b to the 1.2? Yes, but it's complicated how you get to that, so we'll avoid that for now. All right, so this is called an exponential expression. We'll do exponential equations in a bit, where b is the base and n is the exponent. For any number besides zero, so 0 to the 0 is the only one that breaks this, right? For anything, a to the 0 is 1, and then for any a to the minus n is the same as 1 over a to the n, so you can just flip it, okay? So for crunching through that, 5, back to what an exponential means, it means I'm having 5 times 5, right? So that's 5 times 5, which is equal to 25. Here, negative 3 cubed means I have minus 3 times. That's what it means. So I'll have minus 3 times minus 3, which is positive 9, times minus 3, which equals negative 27. Here, if I have a negative number up top, I'm going to write 1 over 3 squared, which is the same as 1 over 9. 0 to raise to any power is 0. Any number raised to the 0 power is 1. And so if I was working with this, here I'd have minus 4 times minus 4 times minus 4 times minus 4, which equals 16 times 4 gives me 56 times 4 gives me 54. No, 16. My brain can't count. 16 times 4 gives me 64, right? And 64 times 4 gives me 256. Yeah, so 256. Oops. All that. So 256, and it's going to be positive because I have the negative 4 times. So if you raise a negative number to an even power, it becomes positive. And raise a negative number to an odd power, it becomes negative. And the only other thing to note that I think we've talked about it already, this is not the same as this. I know we've probably gone over it. This is equal to minus 256 because here the negative occurs after the exponentiation. So that's just something to be aware of. Here we're going to talk about scientific notation for 5 seconds. I don't think I'll actually test you on it. I don't think I'll actually test you on it. But it's nice to know. Here you just count over. So if your periods here or your decimal places here, you just say you always want to make it between 1 and oops, that's wrong. That's wrong. Should be between 1 and get my white. There we go. And less than 10 because you want it to be a single digit. And so here we just move it over 1, 2, 3, 4. So it'll be 5.6789 times 10 to the 4th. Here, when we go back the other way, 1, 2, 3, 4, 5, 6. So 3 times 3.4 times 10 to the minus 6. And here, this is 1, 2, 3, 4, 5, 6. So it'll be 1 times 0, 0, 0, 0, 0, 0, 5 times 10 to the minus 6. All right, so scientific notation is just a nice way of writing what it used to be used for. It was a nice way of writing very large numbers small, right? This technically is a little bit more compact than this. And when you get into like Avogadro's number, when you're doing chemistry, that's a huge thing. Wouldn't it be 10 to the 7? Oh, so no, here. So this one has to be greater or equal to 1, but less than 10. So this has to be a single digit. Okay. So the reason we used to do this is it used to be really huge numbers small. The second reason this has become extremely useful is in computing. So computing, and let me explain why. Because I had to work with something that's on the nanoscale. So I work with stuff that's I work with things that are on the order of 1 to 10 to the minus 9th, right? So I'm doing nano optics. Okay, so that's the scale I'm working with things. Well, when I crunch through in the computer, I can have 1 and 1, 2, 3, 4, 5, 6, 7, 8, and a 1, right? I could have all these zeros, but all these zeros take up space in the computer, which provide no accuracy. Now, if I had, let's say it was like 3, 7, 4, 7, 8, who knows, right? Just whatever my number was for that thing. If I just write it in this form and hold this in memory somewhere else, right? I can crunch just 1.347. And this is easier for the computer to handle, and you maintain accuracy and you don't get overflow. And so scientific notation has a great benefit in computing. They don't tell you this when they first teach you, but now you guys are in college and you actually may work on real computers doing real calculations. You'll see these. And so that's why it's important. All right. So I think I gave you, did I give you homework on scientific notation? I don't remember. I don't think I actually do. All right, so here are properties. If we have two exponentials and we multiply them by each other, we just add them up. So here, if I have 3 to the 4th and 3 to the 7th, I add them up and get 3 to the 11th. Here, if I divide them, I minus the top one from the bottom one. So if I have 5 to the 4th over 5 to the 6th, that's 4 minus 6, which is 5 to the minus 2, which is 25th. Notice here, all these rules can be achieved by just writing them out. You can literally just write them out. So here, if I had 4 3s, and then I had 7 3s, 1, 2, 3, 4, 5, 6, 7. I can count them up to the 11th. Same for this row. If I had 5 or 4 5s up top and 6 5s down below. I can cancel out that, and I'm just left with that. And so the same for these, same exact thing for these. You can just mess with these rows where they come from. If I take a power and raise it to a power, it's like multiplying them. So if I had 2 3s and I had 4 of them, I'd have 8 3s altogether. If I multiply two things, I can distribute in the exponential. Here I can distribute exponentials into fractions, and here if I distribute into negative, I flip them. So here 3/5 to the 7th power is 5 to the 7th, 3 to the 7th. Okay. So let's just crunch through a couple of examples. So here, if I have y to the 4th plus y to the 8th, I'm just going to add them up. So I'll get y to the 12th. Here, if I'm doing this, I'm going to, on C, if I have a 3, I can just put 2 to the 3rd and then x to the 3rd. And if I want, I can simplify this. Here for r to the 7, you have 7 up top and 3 down below, so it'll be 7 minus 3. I'll actually write this one out, which equals r to the 4th. Here, if I have a negative number, I can go ahead and write c to the 4th times negative 2, which will give me c to the minus 8th, which is the same thing as 1 over c to the 8th. Here, if I'm doing this, I can distribute this in. And so I'll have 3 cubed times a squared cubed times b cubed. If I was being very pedantic about it, this becomes 27. This becomes a to the 6th. This becomes b to the 3rd. Okay, and then you'll have what you'll probably see on the exam, right? So this is probably what I'll give you on the exam. So if you have something like this, just clean it up as much as you can and then write it out. So here, the first thing I want to do, the first thing on my list will be to distribute in the exponents. Okay, so exponents go before multiplication. Remember your order of operations. So here I get x squared, y squared. Here I get x cubed, y to the y times 3 gives me y to the 9th over z cubed. Then here, I'm going to just put together what I can. So I have x's on top, so I can put those two together. So I have x to the 5th. Here I have an x up top and or y up top and a y down below. When I put these two together, I'm going to minus them out, so I'll get divided by, well, I guess it's up top, so y to the 7th, because 9 minus 2 would be 7. And then here, I only have z's on the bottom. Looks like this. So this equals x to the 5th, y to the 5th. So yeah. Another way of writing this real quick, let's do this. That's why I'm showing you. These are equally valid. So you can either write it like this or like this. One thing, if I'm messing with lots of exponents, I just put everything up top and just write the negative numbers, and then it just makes my life easier. You'll do a couple of these on the homework. Does that make sense how to do all these? Any questions on any of this before I move forward? The last one, okay. Sure, let me do the last one a tiny bit slowly. Are you okay to this step? I'm just distributing in. Yes, okay, so let's do the next part slowly. So here I have x, and I'm just going to multiply through. X cubed, y to the 9th, all over y squared z3. So I'm just multiplying across to make it a single fraction. All right, at this point, let's handle the x's. So I have x, so these two are multiplied, so I get x to the 5th, y to the 9th over z cubed, y squared. So here, if I ignore this for a second, right, since these are multiple, I can ignore this. I have a 9 and a 2. So to figure out what this is the same thing as this. So I'll get y of 9 minus 2, which equals y to the 7th. And that's positive still, so that still stays on top, which gives me that one. Yeah. Okay, yeah, no, it's really good. It's really good. There's a lot of things. I took this y here. That's where it came from. Okay. I'm glad you asked the question. I really did, because more than one was probably having a question on that one. All right. So this is just moving numbers around in a very particular order. You'll get some practice on this and you'll see an exam question on this. All right, let's talk about radicals. Oh, here we go. All right. All right, so the square root of a equals b. That means b squared equals a, and then b is strictly greater than 0. That's what the square root means. So you're rewriting this is kind of what you're solving in your head. The book lists this. That's wrong. Ignore it. The nth root of a means that b to the n equals a, right? notice here that if n is even, b was greater than 0, and a is greater than 0. If if n is not even, the rules don't apply, because you can have a be negative and you can have b be negative. Okay, but n is still, this is still a natural number, so that's still, we're still going in the positive direction. So another way of writing this, so this is the same thing as, so 16 squared is asking the question, what squared is equal to 16? And of course the answer here is 4. So here, 4. So a little clear. This equals 4 because, because 4 squared equals 16. Okay. Here, let's do this one. This equals, well, what? Well, we want to find out what to the 4th power equals 16. Well, the best guess we have is 2, right? And does that work? 2 times 2 is 4, times 2 is 8, times 2 is 16. Yeah, so this equals 2. Here we have the cubic root. So we're asking here, what cubed is equal to minus 8? Well, here we find it to be negative 2, right? So minus 2. So here, what these questions are asking is what to the 4th power equals the number inside, what to the 3rd power equals the number inside. So that's really what the cubic roots are asking, or the quartic roots. All right, so let's just do some laws of radicals real quick. So since, so we're gonna say that a to the 1 over n is equal to the square root of, or the nth root of a. And so all the same radical laws apply. So and a to the m over n is taking the nth root and raising it to the n power. In addition, if I take a to the n and raise it to the n, if n is odd, is equal to, is a if n is odd, and is equal to the absolute value of a if n is even. Okay, so we'll show all of these by example. Okay, so here I have the 1/2 power of 9. Well, what does that mean? That means take the square root of 9, or, and here technically there's a 2, but no one writes it. So the square root of 9, so that's 3. So the half power is the same thing as saying the square root, right? Let me get rid of the technical too. Okay. Here, when I'm writing this, I'm going to be using this right here. And so here I have x to the 5th. But technically I can rewrite this to the 1/4 power, right? Because quartic root is the same thing as this. And then here I can just multiply, right? Because my exponential rules. 5 times the 4th is equal to x to the 5/4. So here, in my mind, this is simpler than this. Here, let's see if we can't do what we can do. So here we have the 4th root. So let's deal with this. And so technically I can take the 4th root of each of these. So this is the same thing as the 4th root, or the quartic root of 81, the quartic root of x to the 4th, and the quartic root of z to the 8th. Okay. So the quartic root of 81. So what to the 4th is 81? Well, if you work on it long enough, you'll find out it's 3. So here I just get 3. Here, if I have, here I have this situation, right? N and n, so 4 and 4. So n is even, so this is the absolute value of x. Here I have 4 and 8, so this is not the same. So what raised to the 4th power equals z to the 8th? Well, z squared does, right? And so z squared to the 4th, so this ends up being z squared. 3. Yeah, so 3 is the answer. Okay. All right, so let's figure out how to crunch this number here. So here I have 8 to the 8 to the I have 8 to the 2/3 power. Well, can I actually crunch that number? The answer is yes. So here if I take 8 and I take its cubic root and then I square it, what do I get? Because that's the same as this, right? So the cubic root of 8 is 2, and then if I square that, I get 4. So 8 to the 2/3 power is 4. Here, if I have common radicals, I can add them up. So here this becomes 5 square root 3. Here, if I don't have common radicals, I can try to make them common. How do I do that? Well, here I can pull out here, I can pull out a 4, and here I can pull out a 4, right? Can I do better than that? Well, I can do a lot better than that. Let's start with the 4. So here, this is the square root of 30 or so. If I pull out a 4, I get, hold on, I get 4 times, yeah, I can pull out a 16. Let's pull out a 16. Because I get 16 times 2. This comes out to be a 4. And then here, I can pull out a 10 because 10's 100, right? So this becomes 100 times 2, which gives me 10 times square root of 2. Okay. And then now I can add them. So I'll get 14 square root of 2. And so how you proceed with these, let me kind of just say here, if I'm giving you 32, how you proceed is that you pull out squares that you know you can pull out. So here I know I can pull out a 4. So I'll have 4 times, I have 4 times 8, right? And so that was a 2. So I have 2 times the square root of 8. Also here I know I can pull out a 4. So I get 2 times the square root of 8. It's, even if you don't know what to do, just pull out the smallest square you can find. Okay. Here, here I know I could pull out a 4. So let's pretend if I did it that way, right? Instead of pulling out the 10. Let's pretend you can only see 1, right? So I have 200, and I pull out a 4. So it'd be 4 times 50, right? So I pull that out, it becomes 2 times the square root of 50. Here I can see there's a 25. So it'd be 2 times 5 times the square root of 2, and this becomes 10 square root of 2. So either way you pull it out, as long as you can pull out a perfect square, so that's, so if you pull out a 4, it becomes a 2. If you pull out a 9, it becomes a 3. If you can pull out a 16, it becomes a 4. If you pull out a 5, it becomes a 25, and so forth, right? So just try to simplify these as best you can. I give you a couple to do on the homework, and there's kind of a rough one on the exam. There's the one on the exam is a little bit rough. But if you can do that one, I can trust you to do any one ever. Okay. All right. Let's talk about this one. This one again is here. So it's this one here. We have an odd one, so this is just A. So this ends up just being 3. -3. Since this and this are the same, doesn't matter if it's inside or outside, really. Since these two are, nope, technically this is a different beast, but it ends up working out to be okay. I should have written this. But it is the same. This is -3. What do I do when I see this? Well, let's just kind of crunch through this. So let's say I have the square root of x, and then here the square root of x is the same as square root of 1/2. I'm going to work through this slowly. Everyone okay with what I did here? This one I could easily get you lost on. X, and then here I can write this as x to the 1/2 power. So I have that still under the radical. Now I have x to the 1. So x to, if it doesn't list anything, it's 1. So I have 1 plus 1/2. So that is the same thing as x to the 3/2 power. Okay, well, taking the square root is the same thing as taking, so I have x to the 3/2 power to the 1/2 power, which is equal to x to the 3/4 power. I simplify that all the way down. You guys see how I got this one? Yes, no, kind of? Yes, okay. All right, we're all good on that one. And we'll just do this last one here. If I have 27 raised to the negative third power, that'd be 1 over the cubic root of 27, which is equal to a third. All right. So these are all the ways and means we can mess with stuff and do all these things. Before we go and move on to the next section, let me just give you one. Let me just make up a problem in my head. This might go badly, but we'll do it all the same. No, just give me a blank one. I want you guys to crunch through. I want you to crunch through something kind of hard with me once. Yeah, give me blank paper. Why are you not giving me blank? All right, give me half second to make one up because I want you. All right. Because I want to make sure you're ready for the one I give you live Robe for the test. All right. So here I'm going to give you the cubic root of 108 plus the cubic root of 500. Okay. And give this a try. See if you can't put these two together. So give this a try and let me know when someone has an answer for it. Let me double check that it comes out okay. I crafted it so it did. It doesn't mean I didn't make it. Yeah, it comes out as I expected. All right, second someone gives me an answer, I'll go over it, but I'll wait until at least one person gives it to me. Speaking of that, what did I end up putting in that crazy quiz? Because I mimicked the final question we gave last term. Okay, so it's easier than what I've given here, but not too insane. Yes. So what Isabel written's really close. It should be um, super close. It should be to the 1/3 power since it's a cubic root. But let me go over how this was done. Okay. So what do we have here? We have, so here we want to take out cubes, right? So 1 cubed is 1, that doesn't do us any good. 2 cubed is 8, 3 cubed is 27, and then 4 cubed is, we just did this, 64, and then 5 cubed is 125. Okay, so here's our cubes, right? And so forth. But this will get us to what we need to do. Here, can I pull out, well, the one doesn't matter. One doesn't change anything. Is there an 8 here I can pull out safely? This divide by 8, and the answer is no, but it does divide by 27. And so here, if I divide this by 27, I get 4. So I have 27 times 4 cubic root, which is equal to 3 the cubic root of 4. Okay. Now let's do this one. Is there an 8 here? It ends up being no. Is there a 20? No, no. And then here you get this one. This is just 4 times this. And so I have 125 times 4 cubic root. And so this simplifies to 3 cubic root of 4 plus, pull out the 5 cubic root of 4, and this equals 8 cubic root. Do you see how to do that one? I got beat on typing it out. I divided by 4 and got lost from there. So here with the cubic roots, you have to be, you have to pull out perfect cubes. And so once I get this, I get a perfect cube and pull it out. Okay, makes sense. Give it a try. There's a couple on the homework, and if you need me to do one more thing, I did a cubic root on the test, but the test is the cubic roots aren't this big. They're all less than 100. So the things you pull out are a lot easier to see.